My name is Andreas Lood. I'm from Food Radar. It's a Swedish company. We are born out of the question, or out of the task to be able to detect low density foreign objects. So soft plastic was the first thing that we focused on. And our tagline then is making the invisible visible. And I will try to do a quick introduction to this. I'm very glad for Kai for getting some more minutes to talk about this. So what we do is that we utilize microwaves. So this is so different from an X-ray or a metal detector or an optical system. We use microwaves, and microwaves spread spherically. So when you take an X-ray and all those technologies that Kai was talking about now, they're able to sort of give an image of what you see. And in that image, you're looking for what type of contaminant could be in there. We do a very, very different thing. Our microwaves, they sort of go into a pipe, into the product, and they try to find contaminants. And we don't know what it is. We just know that this is something that you normally don't have in your product and you don't want to have. So we cannot make an image of it, or it's at least really complicated to do that. It takes a lot of computational power. But we still believe that the most important thing is that we can kick out and reject those kind of contaminants that you don't want to have in your products. This is very technical, so I'm piggybacking on Kai's nerdiness here, but we are looking at products in a pipe. It's an inline technology. It needs to be a pumpable product of some sort. And when we look at that product, if you take water as an example, water has then a typical density of around 1 gram per cubic centimeter. And then you look at plastic or rubber or wood, which are sort of similar in types of density to this product. So if you're trying to find these kind of materials with an X-ray or with a metal detector or something else, you can just not see them because of the density is so low. But what we don't care about that. We don't look at density. We don't. These numbers are just here to give you an idea. But what we look at is the dielectric constant. So the dielectric of, for instance, Peter's apricot or peach product, when he has a lot of different pieces of apricots in a slurry, then they will have a lot of water content. And that's why they have a very high dielectric constant. But the plastic or the rubber or the wood or the pits of a certain contaminant, they are really, really low on the dielectric scale. So that's why we can see them and why we get the contrast. So we look at the dielectric difference and on the loss of the microwave as it's moving through this medium. Microwaves cannot propagate through metal, so we can see metals and these kind of things as well. But we are always very honest to say that the metal detector or an X-ray can do a better job than the Food Radar can do on those kind of materials. This is a good interpretation of why the microwaves are affected by plastic versus the X-rays are not. So when the X-ray beams are moving through a piece of plastic, it doesn't change the wavelength of those materials, by those materials. Versus in the microwave spectrum, the microwave is actually affected while it's moving through a piece of plastic or to a certain type of material. And this is what we measure. This is what we can detect. We started working on baby food 15 years ago together with Kraft Heinz. That was the first sort of area where they said that we need to find a solution of detecting all these kind of contaminants in that type of product because it's such a sensitive product range, of course. Then quite quickly we ended up in vegetable processing, just because you get a lot of contaminants while harvesting these kind of products. Yeah. So diced tomatoes, diced chilies, diced onions has been a big part of what we do for a long time. We quickly came into the The fruit side, similar problems. All your typical contaminants coming from the harvesting or from the inside the fruits. Yeah. So today we work a lot with all your typical jam and marmalade manufacturers across the world. Your typical preserves and the fruit prep that goes into a yogurt. I know that we had here from Agarana. You have different juices where you have pulps, anything that you cannot strain literally. That's a good fit for the food radar. And then you have the sauce and the soup range, which is massive today. I mean, here you have all your typical types of products. Pasta sauces, pestos, salsas, soups with inclusions inside, anything like this. Now this has been expanding a lot the last few years because we have got so many requests from different other areas. We've had we're working with processed cheese, we're working with instant coffee manufacturers. We had the last 12 months we had a big R&D project together with the world's largest pet food manufacturer with great results for detecting these kind of materials in that. So this is something that is now expanding further, and as Kai said, moving into meats and these kind of processed types of things that you can then process in a pipe. And what can we detect then? So if you see the top row here, hard plastic, soft plastic, wood, rubber, fruit stones or pits, these are kind of the bread and butter of what we do all the time. But we can also detect a lot of other things. So pectin lumps, organic lumps, things that are a little bit to what you said, stuff that are in part of the product, but they are actually not what you expect it to be in terms of the quality of the product. These organic objects that you see here, these are corn cob pieces. Those kind of pieces, but also cotton stick pieces, are very, very common in the tomato industry because they are also harvested from the harvesting. Then you have high density stuff, so metal, glass, stones, especially maybe aluminium from aseptic bags and so on. It's very, very detectable for us. It's a very good kind of contaminant, which is sometimes tricky for X-rays, and metal detectors do a better job. And insects can also be, depending on the insects and a lot on the products and so on. But this is giving you a good idea of what type of foreign objects that we can detect. I want to very, very quickly go through the technology, and I say to everyone here that I'm happy to look more into your operations and your type of products together to look at this to give you a better understanding of what it could look like in your product. But to give you a high level of understanding here, in the left-hand side here, you have a typical food radar. It starts with the bottom part, which is a patented solution from us called an air zip. This is something we had to invent because of air is affecting every kind of inline detection technology. So if you have a metal detector and you get air pockets going through that, it will detect that and reject that, and you inspect it and there is no foreign object. It's just air that was introduced into the process. We can remove that, and it depends on the product and so on, how efficiently it works, but it's a very, very important part of our technology. So first of all, the product is being pumped by your pump through the food radar air zip. Then it goes into the sensor, which is the big part in the middle, or the chunky part. And that's what I want to speak a little bit more about, because that's where we use microwaves to detect contaminants. So that is where we find the different kind of contaminants. And then we have a reject valve, so we just reject that contaminant together with a small volume of product. And inside the sensor then, if I would cut it, then it looks like the first of the three pictures here. It's antennas on the outside of the pipe, and in the middle it's just a circular pipe where your product is being pushed. And we send then microwaves in with these 4 different antennas. We send microwaves. We have like a small phone call through the food, through the product. And when the pipe is empty or the sensor is empty, then it's literally so easy for the microwaves to go from one antenna to another. So, but it's not that interesting. The interesting part is the second part here. You start flowing that product. You start flowing a product through that pipe, and I think we can take your case again, Peter. So if we have here an apricot or a peach product with pieces of apricots, sugar, pectin, whatever goes into that kind of product, yeah. Then what happens is that our microwaves are then going to be disturbed. So you see when the microwaves are being propagated through this product, everything is going to disturb the microwaves. They're going to generate what we call a background noise. And that is perfect because that's that unique product. And this will be unique for every product. And it just takes us a few seconds to learn what your product looks like. And we are learning that continuously. We're adopting all the time. And that's fine because then we know that, okay, this is what your product looks like. This is what a perfect situation looks like. And then we end up in the third situation that suddenly there is a piece of contaminant coming. It could be a piece of plastic like here. It could be a piece of pit. It could be a piece of rubber, anything that is out of the ordinary. And when then the microwave starts propagating through this pipe again, it's affected by that piece of material. So it's changing. It's going to change the properties of the microwaves. And that's what we are detecting and saying that, hey guys, this is something different. This is something that you normally don't have in your product. We don't know what it is. We just know that this is something we need to kick out. And we do this by using 1,000 times less the power output of a mobile phone. So there is no harm for anyone using the equipment or for the product that's being processed in the pipe. So actually, any one of you who goes into the plant with your phone will both heat and radiate the product more. And we don't need any specific certificates or for the operators or education or anything like this in terms of utilizing the microwaves. This is very technical. I won't spend much here, but I want to show you the microwave length, which is the length of the microwave, which is called lambda, has a direct proportion to the dielectric constant. So that's the equation in the middle. And from this, we can derive two equations, basically the loss of the wave as it's moving through a medium, and what's called the refractive index as it's moving through the medium. Both these two, I mean, we are working with microwaves between 2 and 3 gigahertz, so similar to what you have in a phone. And that means that we have up to 3 billion waves per second. So we have a really, really high-speed measurement going on all the time. And what happens then is that we send something like the blue, a perfect microwave. We know what it looks like. We know exactly what it's supposed to be like. That's the blue one that you see on the left-hand side. But we receive something like the red one. So something that has decreased in amplitude. And also the top of that blue one is occurring earlier than the top of the red one. So that's the refractive index. Both these two parameters we measure all the time, instantly in the pipe. And we don't have one microwave. We have those 3 billion microwaves moving per second, which means that we get something like you see on the right-hand side. We get a blue, very, very noisy signal, either in the phase variation or in the amplitude variation. And when you see that spike that's occurring in any one of them, that's a contaminant. That's something that is out of the ordinary, and that's what we want to detect and reject. We have 2 measurement cells. So in our sensor, there is actually 2 measurements going on at the same time. They are totally independent from each other. And this is really, really good from many, many perspectives. But first of all, it's actually giving you an automatic false reject detector. So we need to have a detection in both of these cells to get the object, to classify it as a real contaminant. But also, what we do is that if you're imagining the blue and the red lines that you have on the right-hand side here, the blue one is number 1 cell. So we get measurements, we get a noisy signal because of that apricot product that is now being pushed through the pipe, and suddenly we get a spike. And when that happens, we start a timer. So that's what you see on the with that clock. So we start the timer. We know that, okay, now there is something happening in here. A little bit later in time, that product has moved from cell 2 to cell 2. We are talking milliseconds normally, depending on the flow rate, of course, of your product. And then we detect it again, but now it's later in time. It's a new measurement. It's independent from the first one, so it looks differently. And you get that spike in cell 2. And then we stop the timer. We know now how long time did it take to move from cell 1 to cell 2, which translates into the speed of the object. And that can move really differently depending on what your product looks like, where in the pipe it's moving, and so on. And we use that information to really accurately know when to kick the object out, and also to reduce the amount of rejected volume. Because when you look at an X-ray or a metal detector that you have implemented in your plant, maybe it goes off a few times a day. We will detect so many more contaminants every day at every plant where we are installed. This is just given the nature of what we can detect. So yeah, and anyone implementing this technology are quite amazed by what we can see in the end. The food radar equipment is available in 3 different sizes. So we do a 1.5 inch, a 2 inch, and a 2.5 inch pipe. And the most important thing about this image is that that piece of plastic that you see in the middle has the same size. And the smaller the detector, the smaller the sensor, the better the detection. Because of, if you imagine a cross section or the surface area inside that pipe, it's much smaller in the 1.5 inch compared to the 2.5 inch. So it's much easier to get a deviation of a smaller contaminant in the 1.5 inch versus in the 2.5 inch. And then there are some constraints in terms of what the flow rates that we can handle in each one. But that are more detailed information that we go through when we look at any line anywhere. And as Kai mentioned, and this is probably the most important thing before you, you can ask some questions. Any customer interested in this technology, the first thing we do is to do a proof of concept together with you. So we take a few different products, we run them through the food radar system, and we introduce contaminants, exactly like you see here. So if you see the top picture and you see the first object is always the same. It's a quite big piece of aseptic aluminium material. So it's plastic on both sides and then just a really, really thin piece of aluminium in the middle. That is sort of the reference for us, just to see how we are performing. And for us, we really only need that object. And then we run all the other objects just to verify and see what we can detect and what size we can detect in this particular product. So if you see the object number 2, 3, and 4 are soft plastic pieces. And we start with the bigger one, and then we go down in size and see, okay, what's the smallest one that we can detect in this particular product. And then we create a pilot report, and then that's the further, that's more of a knowledge about decision-making process that you can do internally. And we then have one of these test centers in Sweden where the headquarters for the food radar is, and another one we have in Arlington at the FlexXray facility, where we have this type of machine, so we can do the testing locally in Arlington, or we can bring the machine to one of your sites and do testing on site as well. So, any questions?
Andreas, thank you. Great presentation. I've actually used your equipment in dressings and saucers, so
good,
and had really good success with that. I think I know the answer to this, but I just burnt because air is a problem.
Yeah.
Can you do powder then?
At the moment, we haven't focused our energy on it. We have a good idea of how that could work. It translates the whole process of how we detect things. From now we sort of look at a product that has a high level of dielectric constant, and then we look at the contaminants which are much lower, so that's the contrast. When you look at a powder or another type of product like that, it translates into the opposite. Those products are even lower than the contaminants, and then we need to look at from the bottom and up. But we haven't so far. We are growing rapidly, and we are installing a lot of these machines all over the world. So we have sort of been a little bit too focused on that, and also advancing the technology into being able to handle a lot of other products. But this is something that will come eventually as well. Yeah. Anyone else? Oh.
Just for Jim.
Yeah.
When you do the pilot test, can the company send in samples of common raw material from that they've seen in there?
That's the absolutely best, because then, I mean, we have a huge library of different contaminants, but the best thing is to actually test what your problem is. Yeah. So we know that, okay, we can actually detect those kind of materials that you have. Yeah.
The sanitation, like a CIP process, it just marries up to a process.
Yeah.
CIP process.
Exactly. Yeah. So you just run it's your pumps pumping anyway. So essentially the food radar is a stainless steel pipe. So the product is being pushed through a pipe, and then the microwaves are detecting and reject. Then there is a reject mechanism that needs to be cleaned, but that's also done during the normal CIP process. Yeah. We had some other questions behind maybe.
Yeah, just curious about the feasibility about going to a larger diameter than 2.5 inches. Is that underway, or is there just a limit with radar?
No, so it's the biggest difference if you go to a bigger pipe is that you lose sort of similar to what in the X-rays of slowing down. Yeah, here it's more not so much about slowing down. We can handle a really high speed, but it's just that aperture that we want to go down. But saying that, the actual length of the pipe that you need to reduce in size, it's not that long. So as long as we can reduce a little bit of your pipe going through the sensor and the rejecting mechanism, then the rest of the pipe work can be as big as you have it today.
All right. I hate to cut questions off, but we got to try to stay on time. We got Brian coming up next. Tell you what, we got a close race here for the biggest nerd in the room. So we got one more, and then we'll take a vote. So,
thank you.